So the running time of an algorithm is, this is now, we're going to look at it from the point of view of we already have an algorithm and we just want to see how long will it take. And it's going to change with the size of the input. The bigger the input generally, the longer the algorithm takes. So we're going to use as an example a sorting algorithm called insertion sort, which actually somebody brought up last class. Okay, so the insertion sorting algorithm, this is the algorithm. And I'll just explain quickly how this algorithm works. So let me move this thing around to this board over here. So the way insertion sort, so anyway, we talked already about sorting, right? We decided that we're going to need to do sorting to solve other problems. This is going to be a step for sorting. So suppose we had an array of numbers, and insertion sort kind of works off of this idea. This is a small set of numbers, but suppose we had some of the numbers were in order already. 1, 3, 5, and now we have 2 and 4 to go. So insertion sort works kind of like this. It says this subset of the array is already sorted, and now we're considering where to put this one. So, and this keeps happening until we get to the end. So the way we do it is we have a temporary field. I think in this algorithm they call it the key. And we copy 2 into here. Then we say to ourselves, we're working under the assumption that everything to the left of this number is already sorted. So then we ask ourselves, is this number greater than this number? And if so, copy it to the next spot. Right? So we would write a 5 here. Then we ask ourselves, is this number greater than this number? And if so, copy this one up 1. So we're basically moving everything up 1 to make room for this number, right? Assuming everything before it was already sorted in the first place, we can keep doing this for every number. So then we copy the 3, I'm sorry, the 3 would still be here. We copy the 3 to here. Then we ask ourselves, is this number bigger than this number? If so, we just write it here. If not, we copy it over and go to the next one. Okay, so then we would write a 2 here. And now, after that step, this is sorted, and this is our new number we're looking at, and we want to put that in its rightful spot, right? So we can start this algorithm at the first one, because what we're doing whenever we start with a number, we assume everything before it is sorted, and the new number has to go into its rightful spot. Well, sorting one number is real easy. It's sorted. The second it starts, it's sorted. Then we go to the second one and sort it into everything to the left of it. Then go to the third one and sort it into everything that's left of it until we get to the end. And then eventually, like when we do 4, we would put a 4 here. 5 would get written up here. A 5 would go here. And then we'd move this pointer to here, and then say is 3 less than 4? It's not, so then we put a 4 here. And eventually we're done. Right, so that's the insertion sort algorithm. So what we're doing today is we don't really care, for today we don't really care what the algorithm is. We just want any algorithm so we can analyze it. So we've decided today to take insertion sort. So notice now that we're looking at it, we're starting at position 1 and going till the end of the array. We're taking the position we're currently at, copying that into, this should have been called what should it have been called? Candidate or new number to sort or something like that. So anyway, we call it key. And then we say from the node left to our left, which is j minus 1, go through the whole array looking for swapping the numbers up 1 until we find the spot where key belongs, and then we put key into that spot. And we have to do that for every element in the array. Okay. Right, so this kind of looks like the code would this be considered C++ or Java? There's nothing special about it, right? If it was C++ or C, it could just be code, and if it was Java, it has to be part of a package, like it has to be a static function or part of a class. Anyway, this is like legitimate C or C++ or Java, right? While, arrays, yeah. This, okay. Integer array, yeah, that would be a parameter in either one. Okay, so now our question is this. How much time does this algorithm take to run? If you ran the algorithm and looked at your watch, and how long would it take? That's what we want to figure out. So, one brute force way to do this is to ask ourselves, how long does each line take to run? And this has to do with the speed of your processor and actually even your compiler, if you're familiar with compiling or assembler language. Sometimes a line like this might turn into 3 assembler instructions. Okay, well that's okay. So like so just as a side topic, you know when you buy a processor and it says it runs at 1 gigahertz, it executes 1 gigahertz worth of instructions per second. That doesn't mean it executes 1 line like this per second. The compiler you use might turn this into get the value of the beginning of the array, then get the value of I as a second step, then add 1 to I, then add the beginning of the array to I plus 1 to get the new location. And this could turn into like 5 or 6 steps. Depends on the compiler you use, depends on how fast your processor is, will determine how long this line takes to run. So we're just going to say each of these lines has a cost. Cost 6, cost 7, cost 8, cost 9. It depends on your processor or your compiler. You know, depends on different factors. And 2 years from now, it might run faster because you got a faster compiler or a faster processor. But it has some cost. These lines have a certain cost to them. Okay. Now what we want to do is for every line, ask ourselves how many times does each line run until this thing is done, and just add it all up. Okay, the top line, which goes from j equals 1 to the end, is going to run for every element in the list. This line, where we copy the value of j over, doesn't run the first time, it starts running the second time. So this will run n minus 1 times. And everything in this loop will run n minus 1 times. Okay, the next set of lines is going to run, this is really a summation. For every j, this I thing is going to run, and that's going to run n minus 1 times, but there's a probability. Some of the times we're going to do that swap, and some of the times we won't. So there's a percentage of the time we will do the swap, and a percentage of the time we won't. This is the swap. This part here is the swap. You remember, like we said, if the number we're looking at is less than the one in the array, we'd move it over 1. If not, we just insert it. So how many times this run, there's a luck factor involved. If we're lucky, actually what's the luckiest case and what's the most unluckiest case? In this case, the best case scenario is when everything's already sorted. Because we just look at the number and the one next to it is fine and we're done. If it's in reverse order, then every number we look at, we have to move it all the way to the beginning. And then the next one, we move that all the way to the beginning. So that's the worst case. So there's a kind of a, we'll use T to say there's a luck component. There's a percentage of the time. We're going to do n minus 1. We're going to go, the outer loop's going to go through n minus 1 times. The inner loop is going to go, there's some luck factor involved. Okay, so if we were to take the cost of each line, and then how much time each one takes, we're now going to use the concept of a function. So here's what it's going to come down to. We want to be able to say our algorithm takes this much time, so we can decide if the algorithm is good or not. Right? We were talking about like driving to some location, and how many miles might be the measure of how good it is. We want to say, for algorithms, the more inputs we have, the longer it takes. So we want to come up with a function that says, tell me how many inputs we have, and I will tell you approximately how much time it will take. And the algorithm that takes the least time is considered the best one. So we have, for an algorithm, we're introducing this new concept. We have a time function. So every algorithm has a time function. You give me an n, I'll tell you approximately how long the algorithm takes. So each line runs a certain number of times for each element n, and we have our best case scenario. We end up having the cost of line 1, 2, 4, 5, and 8 run n times, and the costs of line 2, 4, 5, and 8 run one additional time. So now, like I said, this cost could be dependent on your compiler and your processor. This could be nanoseconds or whatever, but if n went off to 10 million, then it would be whatever this number is times 10 million, and this could be some nanosecond thing that you add on to the end. So if we wanted to somehow make a statement that says this algorithm is good or not good, what can we say about the time function? So this is going to seem like a vague concept, but we want to be able to say something like, this algorithm is good because when n gets very large, and we want to say something good about it. What?
It doesn't increase exponentially. You could graph it, basically.
Right, so
one part
basically,
is a constant.
this is an algorithm. Now this is, again, this is the best case scenario. This would be if we got lucky and all the numbers were loaded in sorted order. So this is actually a rare case. We're actually, when we look at algorithms, we're going to look at the best case, the worst case, but more importantly, the average case. Because that's going to happen, statistically, that's going to happen for large n almost all the time. But let's just now look at the best case scenario. If the numbers were already sorted, and we ran this algorithm on them, we want to say something like, give me n numbers and it will take something time. If you double n, the algorithm will double. Like, how would you describe this function? Think of this as one big constant. This is a couple of nanoseconds times n, and then at the end a little cleanup, a one-time cost of a couple more nanoseconds. But if somebody wanted to, if you wanted to describe how good your algorithm is, you say something like, the algorithm, you give me n inputs and I will take what? And how would you say it just in English, not in mathematics? Some way of describing how good or bad your algorithm is. You'd say something along the lines of, as n doubles, the algorithm approximately doubles.
Time double.
Right. It's not 100% true because this piece doesn't happen
start
two
at zero.
times.
That would be like the t-intercept or something, I'm guessing.
Right.
Yes.
Right, from a mathematical
Right.
point of view. So that would be like, it would be a line, but it actually, there's a kind of a one-time cost. Every time you run the algorithm, you have to pay this one-time cost, and then after that, as n grows, the algorithm grows. So it's pretty close to saying, as n doubles, the algorithm doubles. It's not 100% right, but it's very, very close to right. And we want to be able to somehow say that that's true. In other words, we want to say when n gets very large, this part really doesn't matter. And therefore, this is the kind of an algorithm that if the input doubles, the algorithm doubles. But just remember, that's not 100% true, it's like 99.9% true. And this symbol, we'll get to these symbols in a second, this is basically saying that this algorithm approximately doubles when the input doubles. So it means it's basically a linear algorithm. You can run the algorithm on a set of inputs, and then if the inputs double, it'll take approximately double the time.
And unfortunately, will always double, and the bigger n, I mean, it'll always double.
Right, as n doubles.
There's no asymptote to that one.
Right. So this one, right, it doesn't hit a bound or anything like that. Now, what's the worst case scenario? The worst case scenario is if everything's in reverse order. So that meant that inner loop, is going to run not one time for every number, but n minus 1 times every time it gets visited. So if we did the time function for then, we would end up with, at the end, it takes on the form of some number a, which is the collection, it ends up boiling down to, oh, this should be a squared. This should be an n squared. Sorry about that. I copied it from Word into PowerPoint and lost the square. So anyway, it's some set of lines are going to, divided by 2, are going to run n squared times, then a bunch of lines are going to run n times, and then this is going to be that one-time cost of running the algorithm. So the algorithm has a running time that says something like, I took all of these constants and added them all up and called this a. So this is going to be some constant amount of time times n squared. Then another set of stuff is going to run n times, and then another thing is going to run just one time. Doesn't matter how big n is, a certain number of lines have to run at least one time. So if we wanted this, if we wanted to make a statement about this algorithm, what is the vague statement like we just made last time? Last time we said, for the best case scenario, we said if n doubles, the algorithm doubles, which was not 100% right, it was like 99% right. What's the 99% right statement you could make about this case? If n doubles,
You got an exponential.
we have not an exponential, a polynomial.
No, you
An exponential is when you have 2 to the x, and x to the 2 is a polynomial. Okay, we're going to get to exponentials later. But what's the statement that's 99% true? If n doubles, how much will the algorithm take? How much more would this algorithm take? So let's say, for example, n went from 1,000 to 2,000. The algorithm takes a times 1,000 squared is 100,000?
It's 2 to the 6.
2, right.
And n to the 6.
Right, so whatever a is, some constant amount of time to run each of those lines, times,
1,000 times 1,000, 10 to the 3 times.
right, 10 to the 6 is 100,000.
So it's 10 to the 6.
A million.
A million.
A million, okay.
Yeah.
A will run 1,000,000 times. B will run 2,000 times. If we went from 1,000 to 2,000,
So it swamps that.
this one really swamps this one, but this one's growing. So we don't want to totally forget about it. And then this is like the last time, it's just a one-time cost. You can almost neglect it, right? So this algorithm, if you double n, the running time goes up dramatically by this term. This is 1,000,000 times this one with 2,000 times this one. Okay, with 1,000 it would be 1,000 times A plus 1,000 times B plus C. A and B almost carry equal weight. If it was sorry. If it was 1,000. I'm sorry. If it's 1,000, yeah, this term, this is 1,000,000 plus 1,000 of these plus one of those. If n then doubled to 2,000, it would go to 4,000,000. Right? This would be 4,000,000,
Yeah.
2,000, and 1. So if it doubles, what actually, this dominating term went up 4 times in value. This one went up a little bit, and this one stayed the same. And then if this doubled again, this would go up 4 times as much, this would go up a little bit, and so on. So we want to make a statement that is 99% true. What is the statement? It's not 100% true, but if the input doubles, the algorithm takes 4 times longer, plus a little more, but approximately 4 times longer. Right? You know, see how it's not 100% correct, but this term, as n gets very, very large, this term starts to become the dominating term, and this is just a little something that gets added on to the end. So an algorithm, if we wanted to make the statement Well, okay, one way to quantify how good this algorithm is write out this whole equation. And then you have to look at the whole thing and go, wow, that looks like a good algorithm or a bad algorithm. But as n gets very, very large, these terms start to not matter as much. And this is really the dominating term. So we'll use the notation of saying this algorithm, this entire algorithm in the worst case, has a n squared running time. Which is going to mean, what that's going to mean to us is, out of all the terms, the n squared one is the dominating one. There probably are other terms, but as n gets really large, they go away. This is an algorithm that basically, if you double the size of n, the algorithm takes approximately 4 times longer. But that's not 100% right, but it's like 99% right. Okay, so now you could almost argue that that's like shorthand. We want to come up with a way of saying my algorithm is this good. And we're going to just say the running time of this algorithm, its dominating term is n squared. So if you come up with an algorithm whose dominating term is n cubed, and I come up with an algorithm whose dominating term is n squared, we could argue for very large n's, my algorithm is better than yours. Now in really small cases of n, those constant charges might kick in and make one algorithm better than the other. But for very large n's, we're going to say one algorithm is better than the other. So we want to come up with a notation that says the dominating term is this, and we all, as soon as we see this notation, we'll be able to know what that means. So we're going to say we're going to make this statement. This statement says this: a function is big O. This is something you just need to see a couple of times and then you get used to it. A function is big O of g of n. I'm sorry, the big O of g of n is equal to f of n if the following are true. If there is a constant and a particular number n naught such that this function in its entirety is less than or equal to the constant times this function. Now what this is translating into is this. We're saying, you know how some of these algorithms, for small numbers of n, let's say the first 8, one algorithm might be better than another. After 8 or after 20, some small number, n naught. From that point on, one algorithm takes over and dominates the other one. So we're saying for all values bigger than a particular, some small value of n, for every value after that, this statement ends up being true. If this statement is true, then we can say the algorithm is big O of n. You know what? Let me do one example of, I know this looks a little too definition-y. So let me go over an example and then we'll come back to this. So let's see. So I know those definitions look like there's a lot of memorizing going on, but it's kind of getting at the idea of what we're talking about. So if I have an example like this, f of n equals 4 n squared plus 16n plus 3. Now this is a purely mathematical concept. It's in math textbooks, but we're going to use this for computer science. What's the dominating term? Like right away, if n got crazy large, this is going to, however long this step takes, that's going to mean everything. This is going to be like chump change. Okay, what we eventually want to do is we want to make this statement. In the end, our goal is to make this statement. F of n is big O of n squared, which basically means the n squared term is the dominating term. In the end, that's our goal, is to make that statement. So that definition I just showed says f of n is big O of g of n if the following is true. We need to have a constant. So let's say you wanted to ask this question. Is f of n equal to big O of n to the 4? Is this a true statement or a false statement? Now, this is not really a computer science question, this is more of a math question, but is this a true statement or a false statement? It's true if, what does that definition say? There exists a positive constant c and a particular value of n such that 0 is less than or equal to f of n less than or equal to a constant times g of n. And g of n is n to the 4. Can you come up with a constant that this will always be true? And it doesn't have to be true for all n. You could say, well, for only n's 12 and higher. It doesn't have to be for every n, but it has to be for large n's only. It doesn't have to be true for n equals 2 or 3 or something like that. Can you think of a constant you can put here, and this statement will become true? Now, if we put the constant of 1, let's say we decided to let the constant be 1. Is this true all the time? No, right? Because when n is equal to, if n is equal to 1, what happens? 4 times 1 plus 16 times 1 is 20, plus 3 is 23, right? When n is 1, 23 is less than a constant of 1 times 1. That's not true. So, is there any value of n where this will then become true and remain true forever? I'm sorry, this should be an n not. I know this takes, it's a little annoying getting used to this, but once you get used to it, you kind of get what the idea is. Is there some value of n where this term will overtake this whole thing? N was 3?
Well, after that, 23 will definitely be.
Wait, 3 times 3 times 3 times 3 is 81. This would be 81. This would become 81. If we said for all values greater than 3, and what is this? 9 times 4 is 36, plus 3 times 16 is 48. 48 plus 36 is 74, 77. Is that true? That look right?
36 plus 48 isn't it 80?
Yeah, it's 80.
Oh, it's 84, okay. This whole thing is 84?
I was
It's
87.
87, okay. So it's not good, right? But the next one will be fine. If n is 4, this one's gonna take over that one. Okay, so what this formula is saying is, can you come up with a c and a particular value, saying from 4 onward, this is a true statement. It's not true for 1, 2, and 3, but those are for the real, when n is really small. That's where this algorithm might not be good, but from 4 onward, this becomes a true statement. If we can come up with a constant and a particular value of n, from this point off to infinity, this becomes a true statement, then then the statement f of n is big O of n to the 4th is a true statement. That's what this is basically saying. Now, what does this mean to computer science people analyzing algorithms? What this is saying is, if n got really, really big, the dominating term will never get bigger than this. And actually, the dominating term is n squared. So, in other words, this will dominate this entire function when n gets crazy large. That's kind of like what we're saying here. Now, let's make this the question.
Let's see.
What's that?
Well, you use C equals 1, right?
Oh, yeah, actually, you know what, you could have made it easy to pick the bigger C. So when we go and solve these problems, we can pick C and we can pick A.
Right.
And, I'm sorry, and a particular and none. So if we pick, what would be a good C to pick? 100? 100? When n is 1, this is 4 plus 16 plus 9. Yeah, if we did this, that would work. That's a good point.
That's right.
We have the freedom, when we go answering this kind of question, we have the freedom to say, we can pick any C we want and any particular value of n and saying from this point onward, it's true. And if we could do that, then the answer is yes. That means this term is as big or bigger than the biggest term of all of this. That's really what it comes down to in the end. Now, let's find one you can't do. Is this true? N raised to the 1. Okay, now you can pick any C you want. It has to be a finite number, right? Any positive C. So we get to pick a C and a particular n naught. It doesn't have to be true for all n, it just has to, at a certain number of n from then on to infinity, it has to be true. Can we come up with can we make this true? So here's our function n. This is our function n. This is our function g. We get to slap a c in front of it and make c however big we want. Can you think of a c that we could put here that will make this bigger than this no matter how big n gets?
No.
You can't. Is anyone saying you can? Or what if we really took advantage of the fact that this could be any positive number? What if we made this like 1 million?
You have to make n1.
Okay. You mean the particular starting point. This n naught means a particular number, and then it becomes true from that point off to infinity.
Okay. Then no.
If we could adjust that to a bigger number if we need to.
You can't, because eventually n's going to get too big and it's going to
Yeah.
dominate.
Whatever you put in for C, when n gets
It's white.
squared, it's going to take it over. So this, you could never come up with a C n for a particular value of n where this would ever be true. So this statement will never be true. And what this really means to us as computer science people is, we want to say this term is for very large n's. This term will dominate all of these terms, and that's not true. What it really translates into is there's some term here that beats this one. If so, we can't make C big enough to handle this term that's going to dominate us. So what, out of all of the possible things we can put in here, I know this sounds confusing. The first time or two you hear this, it sounds confusing. But what is the smallest thing we can put in here and still get an answer of true? And, all right, let's see if n squared works. N squared, can we think of a constant? Let's see. This is 4n squared plus some more junk, so 4 won't work, right? If I put a 4 here, it won't work, right? Because, oh, I'm sorry, this would be n squared. If I made this a 4, this term will equal this term, and this extra junk will always be more than us. So it's got to be something bigger than 4, right? When we go, we kind of have some luxury here. We can put any number we want. So should we make it 5? Is that going to make the math painful? When n is 1, no, that's not good. And n is 2. When would that become true? What value for n0 would become true? times 4 times 4, and 4 times 4 times 4. This will be 16 more, no, this will still be bigger. And if
square.
And of 10 work? 500, I think 10 will work. This will be 5 times 100, this is 500. This is 400 plus 16 times 4, oh, I'm sorry.
64.
16 times 10 is 160, no good, right? Plus 3, no good. Let's use it then. What about this one? It's definitely gonna happen at some point. So this would be 500 times 10,000. This would be 5 times 10,000. This would be what? 4, a 5 with 4 zeros. And this will be a 4 with 4 zeros plus 1,600. Still no good. Plus 3. I'm getting closer, but should we keep trying this? Could make this one higher. That'll make life easier for us, right? So let's see. If we make this term, I'll make this one by 10 times as much. Suppose we made this 100. And n is 10. Now I'm just doing trial and error, but this would be 100 times 1,000. This would be 100 times 100 is 10,000. This would be This would be a theft. This would be 4,000. Is that right?
400.
Oh, 400. Oh, that's great. All right, we got it. 400 plus 160 plus 3. Okay, there we got it. I mean, we have kind of luxury to play around with these numbers, but all we need to do is say for a particular value of c, and then it doesn't have to be true for all n, just has to be at some point it becomes true and remains true off to infinity. So if that's the case, then this statement is true. So what we're basically saying is this, and this is what it means in English to us. So we're saying big O, a function is big O of another function if we can come up with that constant and the particular number for n naught. Saying it's true from this point on off to infinity. If you want to put the, if you want to swap the functions, you can use this, this is omega, right? Greek letter omega,
Yeah.
okay. This means that the function I'm giving you will always be smaller than your function, which kind of translates into a best case scenario. You could kind of think of this as a worst case scenario and a best case scenario. So, in other words, you can make the statement, my algorithm will always take longer than this function. So this statement up here basically says, my algorithm will always take less time than the function I'm giving you. This one is, my algorithm will always take more time than the function I'm giving you. And if it actually makes it, fits it perfectly, like we said before, we said, what is the best function, what is the smallest function that we can answer yes to, and will never get smaller than it? That's this particular case. So this is the case where the running time of your algorithm will never be, be bigger than, and will never be bigger than or smaller than this particular function. So for example, that algorithm, let's say that was a running time for an algorithm. That algorithm is big O of n squared, and it's omega of n squared. Both of those would be true. It's only true for n squared. It wouldn't be true for any other function. Does that make sense? And so any function, Oh, okay, yeah, let me turn this around one more time. So, if this was now, let's leave the math world, so we change F to T and move to the computer science world. Now it's a running time of a algorithm, as opposed to any random function. We could make this statement, the following statements are true. T of n, the running time of our algorithm. Suppose this was an algorithm. We came up with some code, we ran it, we counted up how many times each line runs. Some of the lines will run n squared, some of the lines will run n times, and then there are 3 lines that always run once. We could make this statement. This algorithm has a running time of n to the 4th. We proved that. It's also true that it's big O of n to the 3rd. It's also true that it's big O of n squared. But it's not true that it's big O of n. This one we said is not true, right? We decided this one's not true. So, if we use the omega notation, we would find that this is true. It's omega of 1. It's omega of n. It's omega of n squared, but it can't get higher than n squared. So what we're basically saying is these terms are tied with or bigger than the biggest term here. That's basically what we're saying. With the omega thing, we're saying these terms are smaller than or tied with the biggest term here. This is smaller than the biggest term here. This is smaller than the biggest term here. This is tied with it. So all of these are true. Now, the other symbol is, was that theta?
Yeah.
Theta means both of these are true. So if your function t of n equals theta of something, I'm going to write a function here. It has to be a function that is true for this and true for this.
N squared.
And there's only one. So it's the n squared one. That means we could find a constant. What that's going to translate into is this. Our function 4n squared plus 16n plus 3 is less than or equal to a constant times n squared and is greater than or equal to a different constant. This is constant 2, constant 1 times n squared. If both of these statements are true, then we can use theta. And you'll find only for n squared can you come up with a constant that will make this, actually this one's easy. What constant will make this smaller than this for all n? 0. It has to be positive. It has to be greater than
1.
0. 1. So if we put a 1 here, this will always be bigger than that. And if we put, what did we say before? Some other number, 10 or whatever it was from before, right? So we could come up with a constant that makes this less than that and a different constant that makes the same function, the n squared, greater than it. We'll only be able to do it for one function because the big O is everything equal to it or bigger, and the, what's that, omega?
Yeah.
Okay. Omega is all the functions that are less than or equal to it, and the only time they meet, this is where they meet, is one, there's only one function where they both meet. And there's only one function where it's true on both sides. And if you think about it, that would be the best way to describe your algorithm. So if we had an algorithm that ran like this, the statement we'd like to, we don't want to make the statement, well, it's big O of n to the 4th. That sounds like a really time-consuming algorithm. We would like the algorithm, we'd like to be able to say it's big O of n squared. That kind of makes it seem more efficient. So that's as low as we can go and still be telling the truth. So really, we're kind of looking for this one. And a lot of textbooks will describe algorithms with this symbol, and a lot of them just go with the traditional big O symbol. But obviously, we want to use, of all the things we could give as an answer, we'd like to use the one that says this is the best way to describe the algorithm. Okay. So this is the mechanism we're gonna use to describe algorithms. We have an algorithm. The algorithm has a time function, which tells us how long it will take if you ran it, like if you looked at your watch and ran the algorithm. The statement we want to make to say if it's good or not is we say the algorithm's running time has big O or beta. Big O of some function or theta of a function. That lets you know, that gives you an idea of how good it is. If you have an algorithm that runs big O of n squared, your algorithm approximately will take 4 times longer if you double the input. If you had an algorithm that runs big O, theta of n, that means approximately if you double the input, the algorithm approximately takes double the time. It's a way of getting an idea of how good your algorithm is.